So first, I explain selected questions from 3 quizzes. 1, 2, 3. Yeah. All right. D.1, explanations for questions in quiz 1, selected questions. Yeah. Some questions I already explained before. Yeah. All right, so look at the question 1. The higher the degree it has, the more multiplication we need. So here, this statement, we want to see if it is 100% true. Yeah. Because we may have the situation, most of the time it is true, but there is some small possibility it could be false. Yeah. When you have situation like that, we should select false. Because when we select true, it should be 100% true. Not most of the time, okay? Yeah. And we know we can find special cases. This statement is not true, okay? Yeah. Here, let me use this question 7 because these two are related. Yeah. So let us discuss together. Question 1, we talk about general formula, but we can consider special cases. Question 7 gives us a special case. And here we know one special case, monomial, n is power of 2, for example, x to the 2 to the kth power, okay? In this way, if we apply repeated squaring technique, then the answer becomes k, right? Yeah, that k number answer. Okay, k multiplications. All right. Then we can extend this repeat squaring a little more to the general case. Oh, similarly, there is a repeated cubing. 3 to the k. Okay. In this case, by repeated cubing. What is the answer? This time not k, right? Yeah. Because this one we need 2, right? Okay. And how about x to the 9th? X to the 9th, we need x cubed, x cubed, x cubed. So we get another 2. 2 times 2. Right? Yeah. All right. So 2 plus 2. How about that? Okay. Yeah, but not time. 2 plus 2 equals 4. All right. Another one. Let's try another one. X to the 27. Right? Yeah. X to the 9th. x to the 9th, x to the 9th, all right? Yeah. Plus another 2, all right? 2 plus 2 plus 2 equals 6. Then you can see for repeated cubing, answer is 2k. How about that? 2 times k, 2 times k, okay? Repeated cubing. Yeah. These two special cases, all right. Then for question number 7, it is 1 plus x to the 6th power, okay? Yeah. And we can treat this parenthesis as one number, but this time, not a power of 2, not power of 3, but we know for the general number, general n, yeah, we can split it into many different ways, right? Yeah, but we can mix power of 2 and power of 3 to represent that general n. In that way, we can make the minimum number of multiplications. But this mixed way, how to mix them, right? Here, in this class, we haven't talked about how to mix. We do not know, yeah. And this question could be very hard. I do not know the answer. So I do not know the answer how to mix. Yeah. So at this point, yeah, because I didn't see anywhere talking about this answer. Yeah. So at this point, I see this as an open question. Yeah, open question. Yeah. And it is quite challenging. Yeah. This open question is very challenging. Yeah. Okay. All right. So that is the review of questions like this. So here you can see we use many pieces of knowledge. Yeah. Repeat squaring, repeated cubing, mix them, and also this structure like Pascal triangle structure, right? Yeah. Pascal triangle structure. Yeah. All these things. Yeah. And in the homework assignment, I give you 2 similar questions. I haven't graded them. Yeah. I will complete the grading by Thursday. So on Thursday, I will talk about homework questions. Yeah. All right, so let us stop here. Yeah, but I hope, I think this case, although we talk about a little bit, but we haven't derived this formula before, right? 2K, yeah. We calculate a few special cases, yeah, but we haven't talked about the general case, the answer, yeah. So I may, since I talked about here, so there is a chance you can expect some questions based on this knowledge in our midterm. Yeah, I haven't thinking about midterm questions. Yeah. All right, next, question number 8. When we apply the greedy algorithms to solve computing problems, do we always get optimal solution? The answer is no. Yeah. The reason, yeah, this question is not hard, yeah, but I like to explain a little bit. Yeah. The reason the greedy algorithms, many problem solvers tend to use the greedy thinking. So it is based on the greedy thinking. People tend to use greedy thinking. What is the greedy thinking? Yeah. So if I use another way to represent it, yeah, at each step, in problem solving, you need to work in many steps. At each step, find a local optimal solution. Okay, yeah, that's the typical strategy. But why local optimal? Why not global optimal? Right? Why local optimal? Right? Because it is relatively easy. Yeah, relatively easier. Global optimal too hard. Local optimal because you only need to consider some local cases in some small local cases. Yeah. Yeah. Consider small local cases. Then it is very relative, much easier. Global cases, too many global cases. Okay, too many global cases. Yeah. So we can not find a relatively fast global solution. Yeah. All right, but local optimal solution, so you put together a sequence of local optimal solutions, you may not get a global solution. Okay, yeah. So each step, best local solution, right? But your step, you can move, in some random way, right? Okay, yeah. Yeah. After you get your destination here, yeah, so your starting point here, end point there, yeah. Then when you look back from your start to the end, the path, the local greedy path may not be the global optimal path. Okay, so the global optimal path. Okay, so that's the main point. Yeah. But why people still use this algorithm? Because sometimes you can get optimal solutions. Sometimes still you have a good chance to get optimal solutions. Yeah. If not, still you can find a solution. At least you can find a solution. How good is the solution? Then you can investigate. Yeah. Because sometimes, even if we do not get an optimal solution, we can take an approximate optimal solution. That's also fine. Approximate optimal solution. Okay. Still, it is valuable. Okay. Yeah. All right. So that's this question. Next one. All right. So this one. Yeah. This one actually is not hard. Yeah, 20. So I give you the exponent number, not too difficult. Yeah, because when we use power of 2, repeated squaring, (16), yeah, 4 multiplications. 20, just one more. Yeah. So this one, I think, pretty easy for you. Multiply x to the 4th. Yeah. All the previous terms you can use. Yeah. But I'm thinking about if I give you a number that is relatively hard for the midterm, yeah, a number, you may need to find a way to represent it. Yeah. Here, I do not know. I need to try myself a little bit. Okay. Yeah. For example, where n equals, let me see, 47. How about that? Okay. Yeah, I do not give you the number too big. Yeah, too big, because that's too difficult. So that n number I like you to try should be less than 100. Okay, less than 100. Greater than 20, let's say. Okay, yeah. If less than 20, that's too easy, right? Too easy for you. Yeah. So greater than 20, less than 100. Yeah. I try to find an appropriate number. Then in the midterm, I give you that term evaluation, the minimum number of multiplications you need to find that answer. Okay. Remember our midterm, the first weekend of November, I will give you 3 days: Friday, Saturday, and a Sunday. Okay, yeah, 3 days. And you may have a few relatively hard questions, like this one. Okay, like this one. All right, so let us go to the next one, part D.2. Yeah, quiz number 2. Yeah. All right. The first question: if an array does not have any inversion, which of the following statements is correct? Yeah. The answer is pretty easy, but here, since it's a review session, right? So I like to talk about questions for this part, inversion related questions. So I also put another question, related question here, unordered, the minimum number of inversions, the answer is 1. Okay, yeah. So here you can see, in the first question, I do not say ordered or not. So an array, yeah. So it could be ordered, could be unordered. Yeah. And then when we look at the number of inversions, okay, yeah, the minimum, this is the minimum, right? Ascending order minimum, this minimum including ordered, yeah, because ascending order, it's ordered. So this time the minimum is 0. Yeah. But for unordered, the minimum is 1. Unordered minimum is 1. So ordered minimum is 0. Descending order, that's the maximum case. So maximum case. Yeah. 1 plus 2 plus and minus 1. Yeah. Remember, in our homework question, our 10 n equals 10. We have that question. Here, the general case, and minus 1. This expression. Yeah. All right. Here you can see the number of inversions should be this one, less than greater or equal to 0, less than or equal to 1/2 n minus 1. Okay, yeah. So the general case, the number of inversions should be in this range. Okay, yeah. All right. Then think about this question. The number of inversions for a given array and the number of comparisons needed to sort this array. Okay. Here, let me raise this question. Okay, yeah. Yeah. What is the relationship between the number of inversions and the number of, sorry, number of comparisons needed to sort the array. Okay, for different sorting algorithm. Because for different sorting algorithms, that the relationship could be different. Think about that. This question is a little deeper, right? Yeah, that means this question is not that easy to answer, but there must be some relationship, right? There must be some relationship based on our intuition. Now here, based on our intuition, the higher the number of inversions in a given array, the more comparisons needed to sort, right? Yeah, that's some rough impression in our intuition, yeah. But it may not be correct. We don't know if it is correct or not. We don't know. That's just our, first intuition. It could be wrong. Yeah. So that's the reason we need to consider different sorting algorithm. Okay, insertion sort, selection sort, bubble sort, merge sort, right? Yeah. So we have learned these 4 sorting algorithms. Yeah. And the relationships in these 4 sorting algorithms could be different. Yeah. And here I just raised this question. At this point, I do not know the answer. So I need to study myself to find the answer. Yeah. All right. Yeah. Yeah. But it's an interesting question. Okay. Yeah. All right. That means there is a possibility if I find some interesting phenomena, I may design a question for the midterm. Yeah. So that's what I mean. All right, yeah, that's what I mean. Yeah. All right. Next, first one, L'Hopital's rule. We can always apply the answer is false. The reason, yeah, we need to check, first check for indeterminate form. Indeterminate, yeah. Okay, yeah. Infinity over infinity or 0 over 0. But for our algorithm class, we just consider, infinity over infinity case. Yeah. Because our growth functions tend to go to zero, go to infinity. Okay. Yeah, not zero case. Yeah. Yeah. And some students missed this condition. Yeah. Because if you see, for example, 1 over n, okay, 1 over n, it's not indeterminate form. The numerator does not go to infinity. All right. So this one, when you consider we convert it to the continuous form, you cannot use L'Hopital's rule. Right? Yeah. No L'Hopital's rule. Okay. Yeah. Because but some people may argue if I apply L'Hopital's rule, I'll get the same answer because the limit is 0. That's correct. Yeah. But your method is wrong. So that means it could be dangerous. Okay. So if you allow that kind of thing happen, you apply a wrong method, but you happen to get a correct answer. If you allow this kind of thinking, sooner or later, you will get wrong answers. Okay, so for our rigorous thinking, we do not allow this. Okay, yeah, we have to make our thinking rigorous. Yeah. The answer is second thing. Yeah. The correct thinking way is the first thing. Right? The correct answer, that's the second thing. All right. Yeah. We want to have the correct answer derived by correct thinking, not by wrong thinking. All right. Yeah. So that's the main point here. Question number 8. It is not hard, but the reason I want to discuss here because I noticed some students still do not know how to do the counting. When you count the number of inversions, how to do the counting? Yeah. The answer is 5, but how to do the counting? Here, I give you some systematic way to do the counting. All right. Because some students may select pairs by observation. If you select pair by observation, you may miss some of the pairs. You may not be able to exhaust all the pairs. So the question is, how to exhaust all the pairs? Right? You need to find some systematic way to get all the pairs. Okay? A systematic way. Then you won't miss any pair. Okay. All right. So let me show you. Yeah. Here, let's do multiple round. The first round with the first element as the anchor. Yeah. Here I use some concept, anchor equals 4. Yeah. Then all the pairs start with this anchor element. Okay, yeah. Consider 4, 2, 4, 3, 4, 1. Okay, yeah. Anchor with the first element. All right. The second round, this time I make this anchor element equals the second element 2, and oh, sorry. Then I run all the possible pairs, but do not look back. Okay, yeah. So here, do not look back. Okay, that's the rule. Okay, that's the rule. Do not look back. Do not consider 2 and 4 because we already consider 2 and 4. Why you look at it another time, right? So 2 and 3, 2 and 1. Okay, do not look back. All right. The third round, this time anchor equals 3. Do not look back, so only look at 3 and 1. All right? Yeah. In this way, you list all the pairs. Okay? Yeah. List all the pairs. You do not miss anyone. But which one is an inversion? Then you just by your observation. Okay? This inversion, inversion, inversion. I assume you know the definition of inversion, right? 2, 3, not inversion, right? Yeah. Because in ascending order, so it's not inversion. 2 and 3 in ascending order, not inversion. 2, 1 descending order, so inversion, right? 3, 1 descending order, inversion. So then you count the number of checked pairs. So the answer is 5 in this way. All right. Yeah. Here I just give you some systematic counting method. Then let me extend it to our midterm question. In the midterm question, I may give you similar question with a few more elements. Okay, yeah, a few more elements. The question is, can you apply the systematic counting way to get a correct answer without missing any inversion? That's the main point. All right, so think about that. Try to understand this method, right? So in the midterm, so I will give you, definitely it will be a little harder than this one, but not very hard. It's doable. It's in a reasonable difficulty. Yeah. So that's the point I like to convey here. Yeah. All right, next one. An efficient algorithm does not have to perform well for the relatively small problem size. Answer is true. Okay. Efficient, right? Because when we talk about efficiency of algorithms, usually we mean the problem size and relatively large. Okay? Yeah. When n relatively small, if the given algorithm doing well or not, it's not that important. Okay? Yeah. So why here I need to explain why not important. Right? Why not important? Because in class I do not have chance to talk about this special property. Yeah, we can treat this as some special property. Okay. The property, this property is related to something called overhead. Overhead part in programming. What's that overhead part? Okay, all right. Setup, right? Data preparation. Okay. When you need to implement your algorithm, you need to do some preparation, right? Arrange your data in a convenient way, to do a lot of things. When you do that part, it takes time, right? Yeah, takes time and a resource. Takes time and memory resource. Okay, yeah. And think about when the problem size n small and large. Okay, when the size small, look at the total execution time you spend. The overhead part takes the larger. So the overhead part, okay, overhead part, overhead part takes, then the algorithm part only takes small portion, right? In that way, if you look at the total time, it could be slow, but there is a big distortion by the overhead. Big distortion. Okay. Yeah. But when the size becomes larger and larger in your total execution time, that overhead part does not grow. The overhead pretty much fixed. The overhead part pretty much fixed. Okay. So then the algorithms part dominate the total execution part, right? So then, as a consequence, the distortion is very small. Okay, so due to this reason, we look at a large problem size. Yeah. So we do not really pay attention to the relatively small problem sizes. Yeah. The background is this: overhead, distortion, resources, yeah. All right, so that is explanations for questions in quiz number 2. Number 3, D.3, yeah. Question number 3, when we solve a computing problem, if we can guess the result that is very close to the real result, it will be very helpful for us to solve the whole problem in a lot of situations. Now, here we just describe some experience in our real world problem solving. Yeah. The answer is correct. In this class, we have this kind of experience several times. We may guesses a few times, right? Yeah. Look at the count binary digits, right? Binary bits problem. That one we make a guess, right? Yeah. And there is another one we may guess. Yeah. I couldn't remember. Yeah. Yeah. Actually, the string matching problem we we make a guess and verify. Okay, think about that, guess and verify. Yeah. And as a general problem solving strategy, so this is a general problem solving strategy. Very useful. Okay, yeah. Especially, this strategy is important in scientific research. Yeah. Think about scientists, how scientists do their research. So they do large number of experiments. From the experiments, they observe many interesting phenomena, right? Many interesting phenomena. So they try to understand those phenomena, okay? They try to find explanations using their theories to find a reasonable explanations. And at some point, they need to make a conclusion or they make a conjecture. They try to guess after large number of experiments, why we always have this kind of phenomenon, right? So then they just make a good guess. Yeah, make a guess. The guess could be wrong, could be correct. Yeah. But then they try to verify it. All right. So that's the general problem solving strategy in scientific research. Okay. Yeah. But in this class, we have some experience for that part. Yeah. I hope in future in your real world problem solving, you may have a good chance to apply this strategy to solve your new problems. Yeah. So here, the value of this class, we want to get a training of thinking. If you learn how to do the effective way thinking, then it could be very helpful to solve your real world problems. Okay. Yeah. All right. So that's this question. Next one, prime factorization. Yeah. So here, based on what we learned, we know this method is, the prime factorization method is very slow. Yeah. So the Euclid's algorithm is much better because for the Euclid's algorithm, we do not have to do prime factorization. Yeah. We get around that prime factorization. Prime factorization, very expensive. Okay. In its time cost. Okay. Yeah. Too slow. Yeah. So here in our class, I couldn't find the time to give you a little more background. I give you some background, but still another part of the background, I didn't have a chance to give it to you. And here I can give you the second part. All right, so we know the prime factorization method, very expensive. The question is it a good thing or a bad thing? Right? So look at this question. So this problem, we know it is a problem, right? Slow computation, this is a problem. But the question is, good thing, good or bad? This problem, good or bad? We know the problem is bad, right? How can you say a problem is good? Okay, you have this kind of problem. But if you change a different view, it could be a good thing, not bad thing. Yeah. So changing your view, it could be a good thing. How can that happen? So that's something very interesting. So I like to give you, yeah, all right. Dual prime factorization is very slow. Here, to be more specific, let me describe. We know this fact. The fact is, okay, doing prime factorization is very slow for, yeah, we know for, here I use huge integers. How about that? Larger, bigger than large, okay, huge integers. Okay, so we know this fact. Everybody knows this fact, okay? So no problem. But the question is, can we make this fact some very useful property for our real world application? That would make it a good thing. We like to take advantage of this fact to develop some real world application that is very useful, very important. Okay, yeah. There is one application, okay? There is one, actually it's a big application. Encryption. You know, encryption is very important, right? Encryption and decryption. In our, internet era, right? Internet era, we know the information sent through internet, we need to do encryption and decryption, right? Otherwise, how do you protect large amount of sensitive data, right? Yeah, it's scary. It's scary. Yeah. So the encryption algorithm, yeah, people need to develop some algorithm, right? And it is non-trivial. The algorithm actually is very difficult. How can you make the strong algorithm to protect your data? That's very hard. Then a group of mathematicians, they notice this fact. They notice this fact. Yeah, extremely hard. Yeah. Even take years for huge numbers, for the supercomputer, even take years to do the factorization, prime factorization. Okay. But they make that behavior an extremely great property for encryption and decryption. Okay, so they develop an algorithm right now still popular, dominant in our current time. They call the RSA algorithm. All right, RSA. The three professors, okay, their initial, last name initial RSA, three mathematicians, put their three initials together. So that algorithm, okay, encryption, decryption, all right, yeah, that one is based on this one. So to do that, you just multiply two large prime numbers. So product of two huge primes. To calculate this, calculate the product, easy, right? The product of two huge numbers using, just ordinary computer is still so easy, right? But the inverse process hard, right? Decomposition. Inverse process extremely hard. Decompose. Okay, by years. To do multiplication. By, let's say, fraction of seconds. Because to do this product by a normal computer, it just takes fraction of seconds. But the inverse process by years, even supercomputer by years. That property is very useful. That means when people do encryption, it is so easy. It is so easy, right? Pretty fast, fraction of seconds, all right? But when hackers, they want to do decryption, they want to break it. In order to break it, they need to do decomposition, prime factorization. That is extremely hard, okay? Yeah, but this RSA method is based on one famous theorem in the number theory. There is a famous theorem. So that's why, because they are mathematicians, so they're familiar with the, number theory. In number theory, there is a theorem called the Fermat's-Little theorem. Fermat's-Little, not the last theorem. Fermat's last theorem, that is the most famous one. But this one is a little theorem, Fermat's-Little theorem. Okay. There is Fermat's-Little theorem, also very famous in number theory. Yeah. And by Fermat's-Little theorem, if you know the key, but you need to know the key, right? Yeah. Because encryption, decryption, you need to have some key. Yeah. So they send that key. They send the key to the receiver side. Yeah. With that key, then apply the Fermat's. Yeah, not just the key. Yeah, you need to get a public key. Yeah, think about that. You need to get a public key, but you also need to have some private phone book, right? Code book, some private. So with that, then you can apply the Fermat's-Little theorem. You can do the decryption. Yeah. But for the hacker side, even after they receive the public key is just this one, product of two huge primes. They cannot break it. If they do not have the code book, okay, some secret part. Yeah, that part is still important. You cannot ignore that part. If they do not have that secret part, then it's very hard to break it, to do decryption. Okay, so that is the background of this thing. Yeah, so very interesting. This thing. All right. Okay, yeah, so that's pretty much although I have one more question, yeah, but this one, actually two more, yeah. Fibonacci number. So the reason I put it here, I just want to let you know we will do our programming project number 2, calculate Fibonacci numbers in 3 different ways. 3 ways. Yeah, I will write, post, modify. Yeah, so modify my old description, but this time I like to, other than the, I like to give you an optional way for extra credit. The optional method, that method is very interesting. Okay, it is described in our textbook. Okay, yeah, but in order to solve it using that one, yeah, you need to pay some extra effort. So that's why I give you extra credit. Yeah. Okay, yeah. All right, so that's the project number 2. Yeah. Then the last thing, remember, we have one small topic left in part B. Yeah. Here, let me complete it. Okay. Let me just use about 10 minutes to complete the selection problem. Yeah. All right. First, the general selection problem. Okay. Yeah. Given an array and a positive integer k. Okay. Yeah. We want to find the kth smallest element. That's the general selection problem. That k could be 1, 2, 3, 4. Okay? Yeah. So k could be the number, the smallest is 1, the first smallest. Okay? The largest is n. Okay? Nth smallest, that means the largest. Okay? Yeah. So that is the general selection problem. Okay, yeah. K, there is a formal name for it. Yeah. Kth order statistic. Okay, its former name. Yeah, and another name for it we call the rank. Yeah. Rank is A. Yeah, rank equals K. Yeah. Another name for it, because it will be easier to call its rank. Okay, its rank is 1, 2, 3, 4. Okay, yeah. All right. And the solution for this problem are very complicated. So here I do not go through the whole solution. I just give you some useful background information, yeah, for questions like this. Yeah. We did one for k equals 1, right? The minimum problem. Finding the minimum. Yeah. So that is a special selection problem. Yeah. Minimum, maximum, similar. Yeah. But there is another special and a very important selection problem is find the median. Find the median. Okay, find the median. Yeah. At this time, our k equals floor function of n over 2, right? Yeah. Because the median, we mean left median, right? Left median by default. Okay, yeah. So that is its rank, n over 2 floor function. Yeah. All right. Here, the data is unordered. Yeah. Think about, to find the median, the data is unordered. There is a question. Do we need to sort the data first? Because if we sort the data, then it's very easy to find the median. But the answer is sorting is too expensive. Yeah. So here, the answer is sorting is more expensive than finding the median. Okay, yeah. In other words, we can find the median without sorting. We can use fewer number of comparisons to find the median without sorting. That is some basic fact for the selection problem. Okay, all right. Should we sort array first? Yeah, so here, what's that? All right, yeah, because here the cost, right? Yeah, sorry, I need to erase. The cost of sorting is n log n. Okay, n log n. If you need to do the sorting, n log n for the worst case. For the worst case, you can use merge sort. Okay, do not use insertion sort. Okay, use merge sort. Merge sort. Worst case, n log n. Okay. Yeah. That means in order to solve the selection problem, we do not consider sorting. Okay, so we need to find the non-sorting based algorithm. Okay, yeah. Here we do divide and conquer. How do we divide the problem? Divide and conquer. Okay, then do the recursion. Yeah. The idea, divide the problem into two subproblems. All right. Drop one of the subproblems. The question, yeah. Drop one of the subproblems. Yeah. That's the problem size reduction, right? Yeah. If we can drop, that's the elimination. Drop also means the elimination method, right? Elimination method here. Okay, yeah. All right. Convert the original problem to one of the subproblems. Yeah. If you can drop one of the two subproblems, you reduce the problem size. Then you do another round, divide and conquer. Okay, similar to binary search idea. Here you can see this idea, similar to that of binary search. Although it is much harder than binary search, yeah, much harder than binary search. But the big picture is very similar to binary search. Okay, all right. But may need to, yeah, so we need to do some analysis on kth order statistic, yeah, because we may need to change it. We may need to change, because when we drop a subproblem, this kth order statistic could be changed. Yeah. So that part is, you know, some details we need to fix. Okay, yeah, all right, yeah. So we need to do conversion, yeah. Because after you drop one of the subproblems, then your kth order statistic could become rth order statistic, different. Okay, rth order statistic. Yeah. All right. Yeah, so here I talk about elimination idea a little bit. Okay, yeah. Yeah, all right. Yeah, because since I do not plan to go through the details of the whole algorithm, yeah, because it's too complex, yeah, too complex. I want to save some time here, then I can talk about other topics. But here, I just give you a conclusion, okay? Conclusion. Okay, conclusion. Yeah. By this elimination method, we can find a linear. What is linear? Big O of n, okay? Yeah, n, linear. We can find a linear algorithm to solve the selection problem. Any selection problem, okay? Yeah. Big O of n, okay, including the median problem. Yeah. So this is the conclusion. So you can see with this algorithm, the algorithm I didn't give you the details, yeah, but you can find it in our textbook. The details is in our textbook. Okay, yeah. So I can give you the reference. So if you want to study the details, yeah, we can find it easily. But the conclusion is we only need linear algorithm, not that big theta of n log n. So it's better than n log n. Okay, better than n log n. Yeah. So you do not have to pay n log n cost sorting the whole array. You can pay smaller, yeah, bigger of n. All right, yeah. So let me complete our part D right here. And we have actually, I need to give you another review session, part E, yeah, part E on Thursday. But after that, I have a quick sort. So after our second review session, we have one last topic of this module 4, the quick sort. All right, so let me complete our lecture today right here.